Welcome to Chemistry World. Now, let us discuss about the tough level problems and tough level examples in a valence bond theory of complex compounds. So, for national level examinations, they will not ask simple sums, they will ask tough sums. So, those who are preparing for advanced exams, those who have the knowledge, average and above average, of course, below average students also they can understand easily. That much of easily I'll explain to you. Sorry, but be careful. These examples are little bit tough to understand and little bit careful to write these examples. You should be very careful. So I'm taking from this is one type of tough level example I'm taking. Like that, we have some examples, some more complexes. For example, MnO4 minus, Cr2O72 minus, and other complex examples also there. Now I'm taking the complexes which have water as the ligand. Here H2O is ligand. In this case, water is ligand. Those complexes where we have water as the ligand, they have some structural differences. They have some different hybridization as compared to normal and simple examples. As compared to normal and simple examples, the complexes way water is present as the ligand, we have some little bit different structures, shapes and hybridizations. Let me see now. Suppose we can divide all these water having ligands. Water has the ligands complexes into three types. First one, M 2 plus or M plus, Mx plus you can say. Mx plus. That M may be lithium plus or beryllium 2 plus. That M may be lithium plus or beryllium 2 plus, and coordination number is 4. Coordination number is 4 means 4 ligands, 4 water molecules are coordinating in this case. If coordination number is 4, if metal is, central atom is lithium or beryllium, definitely the hybridization will be sp3. Hybridization will be sp3 and shape will be tetrahedral. Shape will be tetrahedral. Geometry is tetrahedral, shape is tetrahedral. Both will be tetrahedral. If the coordination number is 4 and the central atom is lithium plus or beryllium 2 plus. And second type is if Mx plus is, in this case M is, in this X plus, that X plus may be whatever the charge, let us see later in detail about that one. If M is transition metals, transition metals means D block elements. If M will be transition metals or main group metals, main group metals. Main group metals means P block metals or S block metals, except lithium and beryllium. Lithium and beryllium, if they are P block metals or S block metals, charge may be anything or transition elements. If the coordination number is 6, coordination number is 6 means number of water molecules in these complexes are 6. Then the hybridization may be D2sp3 or sp3d2. Hybridization may be D2sp3 or sp3d2, and the shape and geometry will be octahedral. Geometry will be octahedral. Please be careful. If the water is present as the ligand in these complexes, that complex may be any transition metal, and that are in these transition metals, they belongs to 3D series. Compulsory, these must be 3D series. The transition metals are 3D series, 4D series, 5D series, 6D series, any 3D series, 4D series, 5D series. Any one may be there. There is no restriction of only 3D series. That may be 3D series or 4D series or 5D series. All transition metals are main group metals, that is P block or S block metals, except the two metals. If the coordination number is 6 and hybridization either D2sp3 may be there or sp3d2 may be there, the shape will be octahedral. And next one is if mx plus is there, in this case, if M is either lanthanoids or actinoids, lanthanoids or actinoids, the M metal may be lanthanoids or actinoids. Definitely, coordination number may be 8 or 9. Coordination number may be 8 or 9. The shape of may be possible in case of lanthanides and octinides. The coordination number may be increased more than 6. That may be present as 8 or 9. The shape of that complex is dodecahedron. Dodecahedral. Dodecahedral shape will be there. Like that, the complexes. You can take any example of transition metal or anything. D2 or sp3d2, that depends upon D2sp3 or sp3d2, that depends upon nature of ligand. I told in previous videos also we have, but exclusively I am saying if water is the ligand in the complexes, lithium, beryllium may also form the complexes. If they are forming the complexes, definitely the coordination number cannot be more than 4. Why? Because they do not have the d orbitals. So they cannot exceed coordination number more than 4. So if the coordination number is 4, definitely hybridization will be sp3. No chance of other hybridization, and shape will be tetrahedral. And if M is transition metal or main group metal. The transition metal may be 3D series or 4D series or 5D series, and coordination number may be maximum up to 6. Up to 6, and the hybridization may be D2sp3 or sp3d2, and octahedral will be their shape. And if metal is lanthanide or actinide, the coordination number may be exceed more than 6. The coordination number may be 8 or 9. In that case, the shape of the molecule is dodecahedral. Like that, examples may be present. So please be careful if water is present as the ligand. Now, let us see some examples. Let me see some examples. First one is VH2O6 3 plus. You can take titanium also as the first element, first example, but I am taking vanadium because in previous exam we have seen, I have seen, and you can observe in previous examples also, we have VH2O6 3 plus was the example. Example 1, VH2O6 3 plus is the example. The name, IUPAC name, all these things, you have to go for that examples. Now, this is the one example is there. Example 1 where water is existed as ligand. Water is existed as the ligand. In this case, I am taking one example. Here, vanadium oxidation state is plus 3 and its coordination number, that is its oxidation state plus 3, and electronic configuration will becomes 3D and titanium 23 now 4s2 3d3 will be there. So 3d2 4s0 will be up here. 3d2 4s0 is the configuration for vanadium H2O6. Here its coordination number is 6 because transition elements can extend their coordination number up to 6 due to presence of d orbital. Remember, they cannot accept more than 6 ligands. They cannot form the bond more than 6. Why? Because they cannot accommodate more than 6 ligands around them. So here 3d2 4s1. Let me take 4p also. Why? Because fourth cell p orbital, d orbital, f orbital also. But we require 4p. So that is, and if you see the configuration, d orbital has only 2 electrons as unpaired, s orbital is empty, and p orbital is also empty. This is the configuration for vanadium plus. Then here 6 H2O are there, so we require 6 empty orbitals. For that 6 empty orbitals, it takes D2sp3 hybridization. D2sp3 hybridization. One d orbital is empty. This do not involve, of course, 3 d orbitals are empty here. So, but D3sp2, like that hybridization will never work. It is D2sp3. D2sp3 hybridization occurs. Why? Because we require 6 empty orbitals. That 6 empty orbitals are possible by D2sp3 hybridization. This D is n minus 1 and this S is ns and this P is np. So inner shell d orbital is involving in this complex. So these are called inner orbital complexes or inner orbital complex. It is not low spin complex. It is inner orbital complex. That's not. Low spin complex means number of unpaired electrons should be decreased. But here number of unpaired electrons are not increasing, decreasing. Same how it was there in a V3 plus before complex formation. After complex formation also same number of unpaired electrons are there. So these are not low spin complex. These are just inner orbital complex, high spin complex itself. So please be careful. It is a tough level I told you. So you have to be very careful like this. So hybridization is D2sp3 means shape will be octahedral. Shape will be octahedral. Remember, the main concept of valence bond theory is determination of hybridization, determination of shape, number of unpaired electrons, magnetic nature, magnetic moment. For these 5 things we use valence bond theory. So here the hybridization is D2sp3, shape will be octahedral, and number of unpaired electrons we have 2. So it is paramagnetic compound because we have 2 unpaired electrons. It is paramagnetic, and magnetic moment if we calculate, the mu equal to root over n into n plus 2 Bohr magnetons. So that is root over 2 into 2 plus 2, then it will be root 2 plus 2 4, 4 2 is 8. Root 8 Bohr magnetons we get, that will be 2.86 Bohr magnetons or something, 878. That exact value is 2.8 something will be there. So like that, this is a magnetic moment, this is number of unpaired electrons, this is magnetic nature, this is the shape, and this is hybridization for this complex. For this complex vanadium. And next, if I take like this, we have examples. Vanadium, it is a previous example, that's why I've used. And in this case only, let me discuss about MnO4 minus structure. Most of the students will be get confused in this. Most of the students and most of the lecturers will say it's hybridization as sp3, but it's 100% wrong. And most of the lectures will say it is a simple compound, but remember, it is not simple compound, it is complex compound. MnO4 is complex compound. Permanganate, the name of this is called permanganate, and its oxidation state is +7. Its oxidation state is +7. Please be careful. In tough level examinations, they will ask the hybridization, coordination number, and all these things. Now let me see. MnO4 structure, permanganate structure. It is a complex compound, not simple compound. Here we have dative bonds, coordinate covalent bonds. Why? Because the Mn7 means, in this case, manganese oxidation state already I told you +7. +7 means 3D0, 4S0, 4P0. 3D0, 4S0, 4P. No electrons in D orbital, no electrons in 4S orbital, no electrons in 4P orbital. Then how it will be in simple molecule? It is not simple. There is no normal covalent bonds in this case. In this case, we have coordinate covalent bonds. So this is 0 and all these things. After that, if you see the structure, orbital structure, 3D is empty, 4S is empty. Remember, 4p orbitals do not involve in hybridization. The hybridization here is, its coordination number is 4. Why? Because 4 oxygen atoms are there in this case. 4 oxygens are there. Coordination number 4 means we require 4 empty orbitals. For that 4 empty orbitals, 3d orbitals, 1s orbital undergoes D3s hybridization. Please be careful. Here the hybridization is D3s, not sp3. D3s hybridization. Why? Because 3 empty d orbitals of 3d, that is n minus 1d, and 1s orbital of ns involve in hybridization. 4 empty orbitals will be arranged in a tetrahedral manner. Tetrahedral shape, and 4 oxygens donates 4 electron pairs to 4 empty orbitals, and MnO4 will be formed like this. 1, 2, 3, 4. Oxygen, 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 oxygen. They are giving electron pairs to manganese. Like this, 4 electron pairs will come towards manganese, and overall is -1 because it's +7 oxidation state. So 8 electrons will become here now, because it is giving one pair. One pair, total 4 pairs are coming, means 8 electrons are there. So but its oxidation state is +7. So that extra electron will be present as -1. If it is +8, it will be 0 oxidation state. But here it is +7. So total 4 pairs are coming towards manganese from the oxygens. That's why -1 will be there. The shape will be tetrahedral, but hybridization is not sp3, it is D3s. Inner shell d orbital and outer shell s orbital form hybridization, and we get that structure. This is MnO4. Due to this, the actual name of this permanganate is, the IUPAC name of this permanganate is, IUPAC name of this MnO4 minus is IUPAC name. It is not permanganate according to IUPAC. IUPAC name is not permanganate. Actually, we'll call it general name as permanganate, but according to IUPAC, it is not permanganate. The actual name of this permanganate is, 4 oxygens are there, so tetraoxomanganate, because negative charge is there na. So manganate, inside the bracket 7 oxidation state, because its oxidation state is 7 ion. Tetraoxomanganate ion, its oxidation state is 7. This is the actual structure of MnO4. MnO4 minus is not sp3 hybridization. Actual IUPAC name is not permanganate. Actual IUPAC name of permanganate is tetraoxomanganate 7 ion. Like that, we have another molecule. We have another molecule, that is Cr2O7 2 minus. Generally, we will call it as dichromate ion. Here also, it is not a simple molecule. It is also coordinate covalent molecule. It is also coordinate covalent molecule, not simple molecule. So please be careful. Most of the students will get confusion in as hybridization as sp3. Of course, in NCERT book it is there as sp3, but actually the perfect, according to valence bond theory, it is not sp3, it is d3s. Same thing, if I take another example, Cr2O7 2 minus, the name of is called dichromate. Name of this is dichromate. Here permanganate and here dichromate. In this case also, chromium oxidation state is +6. Chromium oxidation state +6, and its configuration is 3D0, 4S0, 4P0. 3D0, 4S0, 4P0. No electrons in d orbital, no electrons in 4s, no electron in 4p. Then how it will be sp3? So that basic concept in NCERT level it is there as sp3, but actual according to valence bond theory it is not sp3 hybrid molecule. It is d3s molecule. Let us see how it is, because no unpaired electrons in all these things. And in this case also, d orbital is empty, 1 2 3 4 5. S orbital is empty, p orbital is also empty, but p orbital do not involve in hybridization. P orbital, 4p orbital, np orbital do not involve in hybridization. In this case also same 4, 1 s orbital, 3, 1 2 3. 4 undergoes D3s hybridization, same like that of permanganate. D3s hybridization, D3s hybridization. According to valence bond theory it is. In dichromate also hybridization is D3s hybridization. D3s hybridization. So then D3s hybridization means, why it means, it is coordination number is 4, not 7. Please remember, coordination number is not 7. Here coordination number is 4. And one more thing, it is not a single central atom molecule. It is polycentric molecule. It is not monocentric complex. It is polycentric complex according to valence bond theory. It is polycentric molecule or polycentric complex, because more than one central atom is there in this molecule. Two chromiums are central atoms here, not one chromium. So the two chromiums are linked by one bridged ligand. That bridged ligand here is oxygen atom. The bridged ligand, here one chromium, they are linked by one bridged ligand. That's why the shape of this one will be like this: chromium and chromium, here one chromium and here one chromium, and these two are linked by one bridged oxygen. This is bridged oxygen. Then it has here it is giving one electron pair to this, here it is giving one electron pair to this, and here oxygen on electron pair, here oxygen on, like this, four oxygens giving four pairs to this chromium. And in this case also, one electron pair come from this, one will come from this, and another one will come from this. Like this we have, and its oxidation state is +6. Total electrons, its oxidation state is +6 now. Total electrons coming 8. That's why it will be -2. It will be -2 charge. So according to IUPAC, The name of this complex is, according to IUPAC, the name of this complex is mu oxo, because it's a bridged ligand. It is bridge ligand. It is bridge ligand. So the name is mu oxo bis, because two chromiums are there. So bis, around it we have four oxygens. So bis trioxochromate. 1, 2, 3 is there. Na? So trioxochromate. Why? Because it's negative ion. That's why we have tried chromate. Oxidation state will be 6. Oxidation state will be 6 ion. Bracket close. Mu. Why? Because it's a bridge ligand. Generally, when the bridge ligand is there, according to IUPAC name, we have to say the prefix as mu, and its coordination number is 4, and it is a mu oxo bis trioxochromate. This is actual IUPAC name of dichromate. Dichromate ion. Dichromate is not IUPAC name. Permanganate is not IUPAC name for MnO4 minus. Actual IUPAC name for MnO4 minus is tetraoxomanganate 7 ion, and IUPAC name of dichromate is mu oxo bis trioxochromate 6 oxidation state. That should be in a Roman number in a parenthesis. So I wrote this. This is MnO4 minus ion structure, Cr2O7 2 minus ion structure. According to valence bond theory, they are not simple examples, they are not easy examples, they are not normal conventional examples. So please be careful. So three examples I wrote. One is VH2O63 plus. There inner orbital complex we get, but not low spin. Generally, inner orbital complexes are low spin complexes, but VH2O is not inner orbital, is not low spin complex, but it is inner orbital complex. And here MnO4 and K2, that is Cr2O7 structures. Cr2O7 structures. These are the main examples. Like that, let me see some more examples in next video. Thank you.